Equivalent circuit of practical op-amp. The equivalent circuit of practical op-amp includes input resistance RIN, R0, AOL. These are the circuit parameters. Equivalent circuit of an op-amp includes input resistance Rin, output resistance R0, and open loop gain of the op-amp is AOL. These are the data sheet parameters. These are the data sheet parameters included in the equivalent circuit of practical op-amp. The circuit which represents op-amp parameters in terms of physical components. Op-amp parameters in terms of physical components for the analysis purpose is called the equivalent circuit of an op-amp. The equivalent circuit of an op-amp shown in figure. The circuit shows the op-amp parameters like input resistance, op-amp parameters, input resistance, output resistance, the open loop voltage gain in terms of circuit components like these are the circuit components like Rin, R0, AOL. The op-amp amplifies the difference between the input voltages. Amplifies the difference between the input voltages. Therefore, V0 is equal to AOL into VD. That is equal to AOL into V1 minus V2. AOL is large signal open loop voltage gain. Difference voltage is VD is equal to V1 minus V2. V1 is non-inverting voltage. Inverting voltage measured with respect to ground. R1 is output resistance of op-amp. Op-amp parameters like some input resistance, the open loop gain in terms of circuit components. This is circuit components are Rin, R0, and AOL. The output voltage is directly proportional to difference voltage V1 minus V2. It is to be noted that the op-amp amplifies the difference voltage and not the individual input voltages. Individual input voltage means either V1 or V2. Not amplify the individual input voltages. Thus, the output polarity gets decided by the polarity of the difference voltage. Therefore, output voltage polarity decided by this difference voltage V1 minus V2. The voltage source AOL VD is the Thevenin's equivalent, while R0 is the Thevenin's equivalent resistance looking back into the output terminals. This is the Thevenin's equivalent voltage source and the Thevenin's resistance R0. The equivalent circuit play an important role in analyzing various op-amp applications, as well as in studying the effect of feedback on the performance of op-amp. Feedback is that is closed loop configurations analyzed with the help of this equivalent circuit of practical op-amp. Ideal versus practical characteristics of IC 741 op-amp. These are the some parameters of the operational amplifier: open loop voltage gain, output impedance, input offset current, input offset voltage, bandwidth, CMRR, common mode rejection ratio, slew rate, input bias current, power supply rejection ratio. These two are this one ideal characteristics, and these are the practical characteristics of 741 IC op-amp. Ideal means either 0 or infinity. Practical means some values. These are the practical values. These are the ideal values of the operational amplifier. Coming to thermal drift. Thermal drift means some parameters of the op-amp changes with respect to temperature is called as thermal drift. The important parameters of the op-amp are disturbance the operation of the op-amp are VIO, input offset voltage, input bias current, input offset current. These three parameters are not constant, vary with some parameters like temperature, supply voltage changes, time. The effect of change in temperature on the parameter is more served. Let us discuss the effect of change in temperature on these parameters. First one is effect on input offset voltage. The effect of change in temperature on the input offset voltage is defined by a factor called thermal voltage drift. It is also called as input offset voltage drift. Input offset voltage drift. The thermal voltage drift is defined as average rate of change of input offset voltage per unit change in temperature. Mathematically, it is given by input offset voltage drift is equal to delta VIOS by delta T, where delta VIOS is change as delta T is change in temperature. This parameter change of input offset voltage with respect to temperature is called as input offset voltage drift. That is also called as thermal voltage drift. It is expressed in microvolts per degree centigrade. VIOS is in terms of millivolts or microvolts. Delta means in terms of degree centigrade. The drift is not constant and it is not uniform over specified operating temperature. The value of the input offset voltage may increase or decrease with the increasing temperature. This is the normalized VIOS value in millivolts, represents on y-axis. On the x-axis, ambient temperature in degree centigrade. The figure shows the graph of normalized value of input offset voltage for MC1741 op amp. The input offset voltage is 0. This is 0 at room temperature of 25 degrees centigrade. Referring to the graph shown in the figure, the voltage drift values can be obtained. The thermal voltage drift values can be obtained from this figure. Normalized voltage VIOS in terms of millivolts changes like that as temperature increases. Input, this is called as input offset voltage drift curve. Coming to next one, effect IIOS and input bias current IB. Similar to the input offset voltage, input bias current, input offset current, input bias current and input offset current are not constant but vary with temperature. The effect of temperature on input bias current IB is defined by a factor called input bias current drift, while effect of input offset current IIOS is defined by a factor is called input offset current drift. The average rate of change of input bias current IB per unit change in temperature. As temperature changes, IB also changes. That is called as input bias current drift. The average rate of input offset current change in temperature is called as input offset current drift. Mathematically, these drifts are given by thermal drift in input bias current, thermal drift in input offset current delta IOS by delta T. Both the drifts are measured in nanoampere per degree centigrade or picoampere per degree centigrade. These parameters vary randomly with temperature. They may be positive in one temperature range and negative in another. Figure shows the graphs of normalized values of input bias current and input offset current versus temperature. Input bias current IB is along y-axis and the temperature is on along x-axis. The temperature is range from 0 plus 25 degrees centigrade, 50 degrees centigrade, 75 degrees centigrade, minus 55 degrees centigrade, minus 25 degrees centigrade. At room temperature, the IB value is 0, like input offset voltage. These curves are different for different types of op amps and are generally provided by manufacturers. The input offset current is assumed to be 0 at room temperature. This is the 0 at room temperature. At room temperature, 25 degrees centigrade, the value is 0. Practically no information is available about the change in input bias current versus temperature. There is no information is available on the change in input bias current with respect to temperature. When compensating resistance is used, there is no need to consider the change in input bias current as a function of change in temperature. With this, the analysis is completed.